Okay, so in this video, we are going to sketch a graph of the rational function x over x minus 1 squared. As always, we first find our first and second derivative. So y prime, as we have a quotient, we use the quotient rule. Derivative of x is 1 times x minus 1 squared minus the numerator times the derivative of x minus 1 squared, which is simply 2 times x minus 1 over x minus 1 squared squared, but if you square this, you'll get x minus 1 to the fourth power. We have the derivative we want to simplify, so look on the numerator to factor common terms, and this term share an x minus 1 factor. And as the only common factor between these two terms, and so you're left with an x minus 1 here, minus 2x over x minus 1 to the fourth power. We can simplify this and then cancel an x minus 1 top and bottom, which leaves us with the following. We have here an x minus 2x. This will give you minus x minus 1. So if you factor the negative, you'll have a negative x plus 1, right? X minus 2x is negative x. Negative 1, negative 1. So our numerator will be the negative of x plus 1 over x minus 1 to the 4 minus 1, which is x minus 1 cubed. So we have our first derivative. But we also need the second derivative. So we differentiate the derivative to get our second derivative. Once again, we have a quotient, so we use the quotient rule. The negative we'll leave up front as a constant multiple. And we now differentiate x plus 1 over x minus 1 cubed. So the derivative of x plus 1 is 1 times x minus 1 cubed minus x plus 1 times the derivative of x minus 1 cubed by the chain rule 3 times x minus 1 squared times the derivative of x minus 1, which is simply 1, over x minus 1 cubed squared, which will give you x minus 1 to the power of 6. As always, we now look for a common factor between our two terms. The negative stays up front. We can factor in x minus 1 squared. And we'll be left here with a single x minus 1 minus, we factor the x minus 1 squared, and so we're left with minus 3 times x plus 1. And this is, of course, all over x minus 1 to the 6th power. We can now simplify this term and cancel an x minus 1 squared on top and on the bottom. And so we are left then with negative. Let's see what we have here. Open your parentheses. X minus 3x, so negative 2x. Negative 1, negative 3 times 1, negative 3, which gives you negative 4. Over, if you cancel an x minus 1 squared on top and on the bottom, this one goes away, and you're left with x minus 1 to the power of 4 on the bottom. And finally, we can factor from these two terms a negative 2, which will give you a positive 2 up front, times, if you factor negative 2, you're left with an x plus 2. Over, of course, x minus 1 to the 4. And now we have our first and second derivative fully simplified and factored, so we're good to go. Let's look for possible zeros of our function. So where could where could y be equal to 0? Since y is a rational function, it can only be 0 if the numerator is 0, and of course x will be 0 when x is 0. So we have a single 0 of this function when x is equal to 0. And if you look for the y-intercept, this is the y value when x is 0. Of course, this gives us 0 again. So x equals 0 is a 0 and the y-intercept. Before you look for critical and inflection points, since we have a rational function, we should be looking for vertical asymptotes, right? X is always defined, x minus 1 squared is always defined, but since we have a division, we have to watch for dividing by 0. And this happens when x is equal to 1. So we are going to have a 1 over 0 case, which will give us an infinity case. Therefore, we have that x equals 1 is a vertical asymptote. And now sometimes, we've seen examples where you have a vertical asymptote, but from one side the function goes to positive infinity, and from the other the function goes to negative infinity. So we have to capture what happens around x equals 1 so that we can then produce an accurate sketch. So you have to look for what happens to y as we let x approach 1. Now you'll see sometimes there is ambiguity, so you'll have to look at the limit from the left and the limit from the right. As you will see in this case, there is no ambiguity, so we can simply consider the limit of y as x approaches 1, and you'll see that from the left and from the right will be the same behavior. So we look at the limit as x approaches 1 of y, and our function y is quite simply x over x minus 1 squared. Look at our case. As x approaches 1, x approaches 1 over, as x approaches 1, x minus 1 approaches 0. And there could be ambiguity here as to whether this is positive or negative, but we know it will always be positive because we are squaring it. So we will always have, from the left of 1 or the right of 1, because we are squaring, we will always have a positive 0 case, which will give us always a positive infinity for the limit. So you see that whether you approach 1 from the left or from the right, y will be approaching positive infinity. If we had a case where there was ambiguity, then we would consider the limit as x approaches 1 from the left and then from the right. So we have here our first vertical asymptote, and we know exactly what happens around 1. From both sides of 1, y goes to positive infinity. And this is the only value of x that makes the denominator equal to 0. So this is our only vertical asymptote. We can now look for critical points. Critical points, again, are points where the derivative is 0 or is undefined. So let's look for the derivative being 0 first. If you look, this is your derivative right here. It is a rational function. So the only way for a fraction to be 0 is if the numerator is 0, but x plus 1 is 0 if x is negative 1. So we have our first critical point, x equals negative 1. And because the derivative at this point is 0, at x equals negative 1, the curve will be flat. But we have a second critical point where the derivative is undefined, because if x equals 1, we have a division by 0, and so the derivative will not exist at x equals 1. And this is not surprising because we already knew that at x equals 1, we have a vertical asymptote. So this will always happen. Whenever you have a vertical asymptote, because the function blows up at that point, its derivative will also blow up as well. So this is not a coincidence. The first derivative is undefined. At x equals 1. But this will again always happen. Whenever you have a vertical asymptote, the function going up to infinity will get more and more vertical, so its derivative will blow up as well. So we have two very different critical points here. One point where the curve is flat, another point where the curve shoots up to infinity, so becomes more and more vertical because the derivative, if you look, will also shoot up to positive or negative infinity. What about our inflection points, or possible inflection points? Well, this is the second derivative being either 0 or second derivative being undefined. Let's look at our second derivative. It's right here. And now again, the second derivative is a fraction that can only be 0 if the numerator is 0, therefore if x plus 2 is equal to 0, so if x is negative 2. So we have a possible inflection point at x equals negative 2, where the second derivative is 0, but the second derivative being a fraction is also undefined if x equals 1 again, because we have a division by 0 if x equals 1. But once again, this should not be surprising because we already knew that we had a vertical asymptote at x equals 1. So not only the first derivative blows up at x equals 1, but the second derivative blows up as well. So this is not, again, a coincidence. Well, the only critical point to classify is x equals negative 1, because we know that at x equals 1, we have a vertical asymptote. And we know exactly what's happening around x equals 1. So let's classify now x equals negative 1. As always, we classify critical points with the help of our second derivative. So we find the second derivative at negative 1. Well, let's look at what the second derivative is. It's right here, so we'll get 2 times negative 1 plus 1. Negative 1 plus 2 is 1. So we'll get 2 on the numerator over negative 1 is negative 2. Negative 2 to the 4 is 16, which is 1 over 8. And once again, we don't get it is 1 over 8 so much as it is positive. So the second derivative at negative 1 is positive, so the curve is concave up. And because x equals negative 1 was a point for which the derivative was 0, at x equals negative 1, the curve is flat. And because it is concave up and the curve is flat, we must be having a local minimum. So we know that if we look around x equals negative 1, we will have the curve looking something like this. It is concave up, and because at negative 1 the derivative was 0, we know that the tangent line must be horizontal at that point, and so the curve is flat at x equals negative 1. And again, the only other critical point we had was at x equals 1, but this is a vertical asymptote, and we know exactly what happens to y on both sides of 1. So we're good to go. Now we can construct our table of values. So let's see. We had a 0 at x equals 0. So when x is 0, y was 0. Then we had two critical points, -1 and 1. We know that at x equals 1, y goes to positive and positive infinity on both sides. So we can write here positive infinity to remind ourselves that when we are really, really close to 1, of course f of 1 is not defined. If you plug in 1 in the function, recall that the function was simply y equals x over x minus 1 squared. If you plug in 1 here, you have a 1 over 0. Exactly, that's not defined. But we're writing this to say around x equals 1, y will shoot up to positive infinity from both sides. At -1, if you plug in -1 in here, you'll have -1 over -1, -1, -2. -2 squared is 4, so you'll get -1/4. And of course we have our inflection points, or possible inflection points. One was again the vertical asymptote, and the other possible inflection point was x equals -2. Now, if you plug in here -2, you'll get -2 over -3 squared, which is 9, and so you get -2 over 9. And now, to be able to sketch a graph accurately, you'll have to compare these two values. -1/4 is exactly -0.25. And if you do compute -2 over 9 in decimal form, you'll get -0.2 periodic. So it's approximately -0.22. So it's a little bigger than -0.25. So now we're good to go. We can look at our axes. So x will, along the points that are of interest, go from -2 to 0, or I should say 1. So we'll have a graph that, say, for the x-axis goes, let's say, from -4 to +2 or 3. And we have negative values, but as you can see, they're fairly small. Suppose this is now the y-axis. So let's label our x marks. So we'll go in steps of 1. So suppose this is 1, this is 2, this is 3. This is -1, -2, -3, -4. Now along y, our values range from roughly -0.25 to, well, positive infinity. At x equals 1, we have a vertical asymptote. So we can draw here a dotted vertical line to signify that at x equals 1, we have a vertical asymptote. So we have the point 0, 0, which is right here. Now for along the y-axis, let's go in intervals of, say, 0.5. Or suppose this is equal to, say, 2. This is 1. Then this is 0.5. So let's go with 1 and 2. Therefore, -1, -2. Okay, so then we have the point -1, -1/4. So -1 is right here. So -1, -2, -3, -4. So -1, x is -1, y is -1/4. So it's going to be about here. And at -2, the value is -0.22, so it's a little bigger than this one. So you can just go up a little bit. We'll exaggerate, but it will be a little higher. So we have the point 0, 0, -1, -1/4, -2, roughly -0.22. And the other point is 1, but we know that at 1 we have a vertical asymptote, and the curve will shoot up from both sides to positive infinity. Now, as always, we figure out what the curve looks like around our critical points. The first one being the vertical asymptote. The other one being x equals -1. And we knew, if you remember, that at -1 we had a local minimum. So we will piece this picture at the point x equals -1. So the graph will look something like this here. So it's concave up, but because the derivative at -1 was equal to 0, the curve is flat at this point. Now, this was the only critical point other than the vertical asymptote. So let's see what's happening now. From -1 to 1, this is simply a 0. There's nothing special at that point. So from -1 to 1, there are no critical or inflection points. Because the curve is concave up and increasing, it will remain concave up and increasing, and we know it will pass through this point. And we know that as we approach 1 from either side, and here from the left, y will shoot up to positive infinity. So the graph will look something like this. Now let's look on the left of -1. The point x equals -2 was our possible inflection point. So the curve is concave up here, right? Will this be a true inflection point? Well, we have to look at concavity on the left of -2, and because to the left of -2 there are no other possible inflection points, concavity on the left of -2 will always be the same. So you can evaluate the second derivative at any value of x to the left of -2. So we'll look here at -3. So if we look at the second derivative at -3, well, let's remind ourselves what was the second derivative. It's 2 times x plus 2 over x minus 1 to the 4th power. So at -3, we'll have -3 plus 2, that's -1, times 2, -2, over -4 to the 4. So the second derivative at -3 is -2 over -4 to the 4. But because 4 is even, -4 to the 4 is positive, and this is negative. And again, don't bother finding the value of this and simplifying. All we care is the sign of the second derivative. Will we have concave up or concave down? Because the second derivative is negative at -3, the curve will be concave down around -3. So we look at our picture now and we say, well, there really is a change in concavity, because to the right of -2, the curve is concave up, right? But to the left of -2, say at -3, the curve is concave down. So -2 is a real inflection point. So and I'll make the curve a little flatter here. the curve is flat. At x equals -1, it's concave up, 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 until we reach -2, because we know that at -3, to the left of -2, the second derivative is negative, the curve is concave down. And so the curve will go from concave up to concave down. So concave down, and then concave up. And we know that to the left of -2, there are no critical or inflection points. And you can see the curve will therefore be decreasing and concave down. So it will be decreasing and concave down forever, to the left of -2. The only question is, since there are no critical or inflection points, or asymptotes, to the left of -2, the curve will never change its behavior again. We still have to answer the question of what happens to y as x goes to -infinity. Will we have a left horizontal asymptote? Well, let's see. Limit as x goes to -infinity of y the function was simply x over x minus 1 squared. And as x goes to -infinity, we have a -infinity over, since we square it, we'll have a positive infinity. And here you have two options, right? Since you have a rational function, you can simply divide top and bottom by the largest power of x, either on top or on the bottom, and then let x go to -infinity, or you could use also here L'Hopital's rule. Because we have a simple rational function, I'll use the method of dividing top and bottom by the greatest power of x, either on top or on the bottom. So I have a single x on top. If I expand this on the bottom, I will get x squared, -2x plus 1. And so I'll do 1 over x over 1 over x. You could also do 1 over x squared over 1 over x squared. We work out the same. Because 1 over x over itself is just 1, let me multiply through now, and then we'll have the limit. We'll have 1 on the numerator over an x minus 2 plus 1 over x. As x goes to -infinity, 1 over x shrinks to 0. And x goes to -infinity minus 2. So this will give you a 1 over -infinity case. The result will always be negative, but as you divide 1 by something which is getting bigger and bigger and bigger, the fraction will be getting smaller and smaller and smaller, and it will shrink to 0, but always negative. And as we can see from our picture, so we see that y equals 0 is indeed a left horizontal asymptote. As x goes to -infinity, y is getting closer and closer to 0. Always, of course, from the negative end. So we have a left horizontal asymptote in y equals 0. So as we keep going to the left, the curve will always be decreasing concave down, but it will be getting closer and closer and closer to the x-axis. Right? It should be smooth, decreasing concave down. This is a rather bad picture, but decreasing concave down until we hit -2, and then it changes to concave up, but still decreasing. So y equals 0 is a left horizontal asymptote. Okay, the only thing left is, well, what happens to the function to the right of 1? If you look to our table of values, we only have values of x up to 1. Beyond 1, we have no information. What's great, though, is because above 1, there are no critical or inflection points, the curve will never change its behavior again. So if we find what happens to the curve at one point in terms of increasing versus decreasing, concave up versus concave down, it will be the case for every other value bigger than 1. So let's figure out what happens to the curve at 2. Is it increasing or decreasing? Is it concave up or concave down? And then we'll be good to go. So we'll have to add. And again, will the curve be positive or will it be negative? Right? So we'll add another x value, which is x equals 2, to get a better accurate picture of what's happening to the right of 1. If you plug in here 2, you get 2 over 2 minus 1, which is 1 squared, which is 1. So you get, when x is 2, y is 2. And now again, we want to know if it's decreasing, increasing, concave up, concave down. So we will evaluate the first and second derivative at 2. So if you go back, this is the first derivative. 2 minus 1 is 1 cubed, which is 1. 2 plus 1 is 3, so you get the first derivative is negative 3 when x is 2. What about the second derivative? Well, here it is. At x equals 2, again, 2 minus 1 is 1. 1 to the 4 is 1. 2 plus 2 is 4, times 2 is 8, so it is positive 8. And again, we don't care about the values themselves, but just their sign. So the first derivative at 2 is negative. The second derivative at 2 is positive. So both imply that at x equals 2, the curve will be decreasing and concave up. Well, if you think of it, decreasing, there are only two ways to have a decreasing function. Either it is decreasing concave down, or it is decreasing concave up. We know it's concave up, so the curve will look like this around x equals 2. So we go back and then we glue this around x equals 2. So the curve will look something like this. And if you think about it, we know that as we let x approach 1 from either the left or the right hand side, so here we are approaching 1 from the right, y will blow up to positive infinity. So as we're getting closer and closer to 1 from the right, y will be getting closer and closer to infinity. So we'll keep increasing and approach this vertical line, which is our vertical asymptote. We know now that the function, since there are no critical or inflection points, will remain concave down, concave up, and increase and decreasing forever. The only question left now, as we know it will be decreasing and concave up forever, will we have a right horizontal asymptote? So what happens to y when x goes to positive infinity? Well, let's see. We have an infinity over infinity case. So you could again use L'Hopital's rule, or you could simply do what we did for the first limit, multiply top and bottom by 1 over x, and you will find that you get the same limit. This will be equal to 0. So as x goes to positive infinity, y approaches 0. So y equals 0 is also a right horizontal asymptote. So I'm a little too high here, but we know that if I would correct my curve, it would look more, maybe more something like this. Concave up, decreasing, and in the limit, y will be approaching the x-axis because this is the y value equals 0. And we know that as x approaches positive infinity, y will be approaching 0. So the curve will go like this. And as x becomes bigger and bigger and bigger, y will keep getting smaller and smaller and smaller and getting closer and closer to y equals 0, therefore the x-axis. So we have both y equals 0 as a left and as a right horizontal asymptote. And now we have completed the sketch of our function. So let's specify that y equals 0 is also a right horizontal asymptote. What else do we have as a key feature of this graph? Well, clearly x equals 1 is a vertical asymptote. If you look at x equals -1, this was initially classified as a local minimum, but if you look, it also is a global minimum. Nowhere else will the function ever attain a value smaller than -1/4. So this is our global minimum. And we had x equals -2 as a possible inflection point. And indeed it was, because to the left the curve is concave down, and then we hit -2, the curve becomes concave up. So x equals -2 is an inflection point. And there was, if you remember, another possible inflection point given by x equals 1. The second derivative at x equals 1 was undefined. So is the vertical asymptote, x equals 1, also an inflection point? Well, let's see. Is there a change in concavity? To the left of -1, the curve is concave up. To the right of -1, the curve is also concave up. So x equals 1 was only a fake inflection point. It is only a vertical asymptote, not an inflection point. You will see examples where sometimes a vertical asymptote, giving you a point where the second derivative will also be undefined, will turn out to be an inflection point. So you may end up with a function that looks like this to the right. So then you'd have concave up on the left of your vertical asymptote and concave down on the right, and then there will be a change in concavity, and your vertical asymptote, x equals 1, would also be an inflection point. But in this case, it is not, because on either side the curve is concave up. And so we now have an accurate sketch, omitting my screw up here and here, of the function x over x minus 1 squared. And again, this is really non-trivial, because I don't think you could have guessed that the graph of x over x minus 1 squared would look like this, with a global minimum at -1, an inflection point at -2, two horizontal asymptotes being y equals 0 on both sides, a vertical asymptote at x equals 1. So if you smooth this out, you have a really accurate sketch of this function.